Good afternoon, ladies and gentlemen. Thank you for coming back after the wonderful lunch. My name is Yuri. I work for the Aviation Bureau, and amongst other things, I do management stuff, boring budget stuff. But when my family asks me what I do, I tell them I do commercial space and new entrants. So this is the panel on new entrants, and to lead us through this difficult but new area, or the simple but new area, is the familiar face, Nancy Graham, who many of you will have known when she was director of the Aviation Bureau here in ICAO. And she is going to take us through this path. Just one note, when she was here as director was when we had the first GANIS, because it was important for us to listen to what the industry did before we set the regulatory strategy down its path. So this is kind of a putting Nancy to a place where something that she had herself created can help us move to the next generation. So thank you very much. Please welcome Nancy Graham.
Thank you, Yuri. How are you going to get down, Yuri?
I'm going to jump.
You're going to jump? Okay, ready, set. Okay, he did it. All right. Good jump. Good afternoon, everybody. Thank you for coming to this session. Just a few minutes of introduction to this particular session. ICAO, through the Chicago Convention, was established, and I quote, promote cooperation and create and preserve friendship and understanding among the nations and peoples of the world. And since 1944, ICAO has done that predominantly through the development of standards and the enforcement of those standards through the audit program. Notice that I said to promote the cooperation and friendship among peoples, not just to move people around, but to quote cooperation and friendship. It's going to be important for the future. ICAO created this venue, as Yuri said, to enable the aviation industry to tell ICAO, its regulators and air navigation service providers, what its plans and needs are for the future. And I'll tell you, the first time we did this, industry was a little surprised. They're not often asked what their needs are. So maybe they were even a little bit shy. They weren't used to being asked, but now they are, and they're not shy anymore. And what you're going to hear is some not shy, interesting promotions. So we're now in a new era. We're not at the beginning of that new era. We're in the new era. In fact, what you'll see today and tomorrow are a triad of new entrants. Outer space is being explored with state-sponsored public funds, and increasingly through private companies and private funds. You'll hear more about that in panel 3 tomorrow. UAVs and drones have become ubiquitous in our language. Who could have predicted the explosion of small drones, forgive the pun, and the myriad of missions that they're currently supporting? While ICAO was unable to take on the standardization of the quote-unquote small drones, you'll see that the innovation has taken place nonetheless. I congratulate ICAO for the recent Drone Enable event. They're on the right path for looking at really what the challenges are and how ICAO can embrace what's happening in the industry. They're helping to promote the best practices and learning from one another, from continent to state, and sharing that information. You'll hear from the traditional aviation manufacturers with new craft, and also from what's called the disruptors, only I personally don't like that term. I think it infers something negative, and I think it's really indeed something positive. In fact, the disruptors are the next generation, this generation of aviation talent, bringing in new thinking, new talent, and yes, new money into aviation. So panel 3 is space, panel 2 is drones in some fashion, both in controlled airspace and segregated lower airspace. But first today, you're going to hear about the operations that are currently ongoing and planned for the middle, what I call the new frontier. The new entrance in upper space, upper airspace, or inner space. That's above flight level 600 and below what's commonly referred to as the Kármán line, or roughly 100 kilometers. So what are they doing up there? Let me set the stage with a couple of surprising pieces of statistic for you. One of the uses of upper airspace in the stratosphere is hosting floating platforms like cell towers through one type of craft or another, you'll see several here today, designed to promote the cooperation and create and preserve friendship and understanding among the nations and the peoples of the world. It is a part of your mission. By enabling the telecommunications and internet in remote and underserved areas. Not only is this consistent with ICAO's Chicago Convention, but it's also key to the United Nations sustainability goals and very consistent with ICAO's own No Country Left Behind initiative. We know that less than half the world's population have reliable access to the internet. And yet this access in developing economies generates 2.2 trillion in additional GDP and a 72% increase in GDP growth rate, and more than 140 million new jobs in those developing economies. We know that this access can increase crop yields, up to 50%, and can improve health literacy. For example, Google says 1 in 20 Google searches are health-related. The telecommunications industry itself is a $5 trillion business. Trillion, I said, dollar business. And the high-altitude platforms that you'll hear from today themselves are a $121 billion business. And finally, most countries have a national goal in some fashion of internet access for their citizens. You'll hear from Google Loon, already operating and providing service, Thales and the Stratobus project, Facebook and their Aquila project, Airbus with their high-altitude platform, all planning very near-term operations. You'll then hear from a company called Boom. I love that. It is one of the 4 supersonic aircraft manufacturers called Boom. That's good, don't you think? And then you'll listen a little bit to Worldview, who are sharing their plans for stratospheric inner space tourism. Who wants to go? I do. After the break, you'll hear from one of the leading universities in China about their views on the global legal framework as it relates to upper airspace, as it is today, and what we may need to do to support these global operations. And finally, you'll hear from both the FAA and Eurocontrol about how their early thinking and planned collaboration on an upper airspace concept may come to light. Know that more than 40 countries around the world today are already providing air navigation advisory services today. And that will only increase based on market demand in those particular countries that need these internet services. As you listen to these speakers, recognize that for most, this is their first time to ICAO. While you're learning about their operations, they're learning about what they may need from you to make their operations sustainable and allow for growth. For those of you that are from civil aviation authorities and air navigation service providers, please listen to what they're going to share with you with this in mind. Do you know enough, do I know enough about the new entrants to help them enter service safely? And how do I learn more? Do we as an aviation community have enough experience in developing performance and risk-based regulation to enable these new things? How do we share that information across states and across continents? So we are in the new era, and with that, let me introduce Alistair Westgarth. He's the Vice President of Project Loon, and the first to talk about their ongoing and planned operations. Thank you. Alistair, over to you.
Thank you, Nancy. Thanks, Yuri. As Nancy said, my name is Alistair Westgarth. I'm the head of Project Loon. Some people would know us as from Google X or Google. It's actually called X, but Project Loon is one of the projects within that community of X. And as Nancy alluded to, what we do is we use high-altitude superpressure balloons to haul communications payload up into the stratosphere. Less than half the world has ready access to the internet, broadband access. A stat Nancy already threw out there, you give internet access to a farmer, that can increase crop yields by 50%. A 10% increase in broadband access can move GDP by 0.15%. So it's a very, very powerful enabler of what people can do to improve their lives. Now, even though half the world doesn't have access to ready broadband, they'll go to amazing lengths to try and reach it. Some examples that we've seen firsthand and personally. In Brazil, commonly we see people climbing up a tree, doing the classic holding the phone up in the air, trying to find that signal so that they can download homework, connect to the internet, do something that would actually change their existence. In Peru, there's a real picture of people driving hours per day to get to internet access so they can apply for a job, download schoolwork, connect collect agricultural information or whatever. We had even cases in Peru where people would drive 3 hours from a village to a town to press their phone to a metal statue of the Virgin Mary so they could get connectivity. Not made up stories, absolutely true. And one of my favorites, one of the most innovative things I've seen, in the DRC, an individual built a tree fort to go up a tree to get high enough and then charged access to that tree fort so that people could get access to the internet. So it is literally becoming like shelter and food. It's an essential of modern day life. And why should we avoid having it provided to the other 50% that don't have it today? So we came up with a solution, crazy solution. One of the things that we do at X is look at really hard problems, 50% of the world not having access to the internet, come up with a crazy, fantastical solution, and try and find technology that we can connect to it. So what did we think of? We thought of balloons, mobile phone towers in the sky. Why can't a tower be 20 kilometers in the sky versus 200 feet in the sky? So picture one of our balloons in New Zealand with the Alps in the background, but it gives you an idea of maybe what can be done. Also, connecting the unconnected, it's endorsed by the UN via their Sustainable Development Goals, specifically in our case, number 9 on infrastructure, number 17 on partnership around the ICAO with no country left behind. Let's not leave anybody behind. And also, we're not trying to provide connectivity in Montreal, Nairobi, San Francisco, London. We're trying to provide connectivity to those people that don't have it today. So these things need to be self-sustained. They're solar powered. We use batteries for operation during the evening. And down in the bottom half of that photograph, you'll see a flight up in the air, 60,000 feet, 20 kilometers up, and it auto-configures, automatically makes the connections to our ground stations and the users on the ground. Okay, this crazy idea of using balloons for connectivity, how does it work? People ask me about the propeller on the balloon. There is no propeller on the balloon. We steer by changing altitude. We go to different wind currents. We take the weather data from around the world, weather data here from Europe, weather data provided by NOAA, NWS in the US, and we know where the air currents are. And we go up and down around the FL600 layer so that we can find wind currents that go north, south, east, west, so we can go to the direction we want to go and maintain our position over the target that we want to serve. And also, we're able to cluster balloons. So it's not just balloons randomly flying all over the place, but they're going to a target region. They're going to Lima, they're going to northern Peru, they're going to Puerto Rico, they're going somewhere in Africa, but they're going to a specific area so they can provide connectivity. And it's direct to handset. One of the things that we realized early on in the project at Loon is we can't ask somebody that has a very low monthly income to buy a new device. It has to be the device that's sold to billions of people already and has the best economies of scale, so it's a direct-to-handset. So there's no difference in experience using a Loon-powered internet experience versus, say, connecting to AT&T or Telefonica. It looks the same. It doesn't say Loon on your phone, it says AT&T. It says Telefonica. Also, our balloons connect from one balloon to another balloon. So our ability to reach remote areas is significantly enhanced because of that capability. So when we first started this out, we really had no idea what we're doing. If you look at the bottom picture in the left-hand corner there, it's literally a latex rubber weather balloon, about 4 feet across, pulling up a cut-up beer cooler with a Linksys router inside it. And then we chased it with a pickup truck and a Yagi antenna to see if we could make a connection. Not a very scalable, not a very powerful solution, but it was sort of the start of the adventure in 2012. Now you look at the larger picture, this is one of our commercial operations in Puerto Rico, where we have this semi-automated launch process where we can launch a balloon the size of a tennis court every 30 minutes. That's controlled from our mission control in California and Mountain View and is coordinated with the local air traffic control so they understand and know what's occurring when the balloon launches. And now we know how to navigate. When I first got involved in this project a little less than a year ago, I was like, steer balloons? That sounds a little crazy. But with our software, we're able to find these wind currents that we want so we can steer where we want to go. And so we can launch a balloon in Puerto Rico and 12 days later have it show up in Peru and stay in Peru for 100 days. You look at the original idea where we're literally going to blot out the sun with so many balloons flying around the equator with the rubber band. That's not a very scalable business proposition. But remember what I said earlier, at X in Project Loon is about a big problem with a fantastical solution and applying technology to that solution. I've got a brief video of some of the experience that we've had recently, early part of this year in Peru.
This is the first time Loon has tried to deploy in a disaster scenario. We know that Loon has tremendous advantages for these types of settings, but we haven't had an opportunity to go out and make a difference in a disaster.
Every time I see that, I'm inspired. You know, it's very important to mention, we could not have done any of that without cooperation from our friends, our colleagues, the government, the aviation authorities, the communications authorities in Latin America, whether it was Peru where we actually provided service or any of the countries that we flew over. So thank you to any of the members from those countries that are here today. So we've done it once. We literally scaled up from 25 users in January, December of last year to hundreds of thousands of users in Peru. And we still are operating service there today. And it's in concert with our partner there, Telefonica, working very tightly with both the communication authorities and the aviation authorities. So we did it once. Could we do it again? We didn't plan for multiple disasters to happen, but in Puerto Rico, many of you would have known all the hurricanes that hit the Caribbean this year. There's 5 hurricanes that walked through the Caribbean. And then Hurricane Maria was a direct hit on the eastern end of Puerto Rico, literally 10 kilometers south of our launch site where you saw that picture earlier of us launching balloons. So we thought, okay, we want to do it again in cooperation with the FAA and the FCC to make sure that we could have both spectrum and ability to fly and operate service in Puerto Rico. And this is from our launch site in Nevada, because our launch site in Puerto Rico was damaged. We brought it back online now, but at the time, we couldn't use that launch site. And it is ironic, we launched balloons from Puerto Rico to serve Peru, then we actually peeled some of the balloons out of Peru and sent them back to Puerto Rico so we could provide service in Puerto Rico, plus the ones here you see that we launched from Nevada itself. Again, a brief video. Yuri?
Hi, my name is Pedro Manueli. I'm an auto launch specialist for Project Loon here in Winnemucca, Nevada. Currently in Winnemucca, we're launching balloons out of this crane back here towards Puerto Rico to be able to reestablish connections and connectivity to the people of Puerto Rico who lost all their connectivity during Hurricane Maria. I'm from San Juan, Puerto Rico, born and raised. I'm currently here trying to help out and give my part to be able to give those people that connectivity they need to be able to communicate. Being Puerto Rican, this is very a special opportunity and very proud moment where I'm not only helping the world, but I'm helping home. I'm helping my people, I'm helping my family be able to connect and be able to reach out to those families that are maybe living in the States or maybe in remote areas of the island that are still without connectivity. So it's a very proud moment, very special, and makes me feel very proud of what I'm doing here.
And again, we couldn't have done it ourselves. The government of Puerto Rico, FEMA, U.S. military, AT&T, T-Mobile, FAA, FCC were essential in us being able to provide the assistance that we provided. Here's a picture after we got going. 6 balloons providing coverage across the bulk of the island. So we've now connected well over 100,000 people, moved terabytes of data, and it was great when we saw the CIO from Puerto Rico and he had a screenshot of his phone and he held it up. He says, when you guys showed up and I finally had service back on the island again, I took this picture so I could show people we actually had connectivity again. But we're not done. Puerto Rico, Peru, we're spending a lot of time testing in Africa now. That's one of the next frontiers that we want to conquer. Here's a specific example where we flew out of Nevada, went to Peru, provided service in Peru for a while, then another 12 to 15-day journey over to South Africa. We've flown into many areas in Africa, but it's an interesting area that we definitely want to invest our time and effort in 2018 and beyond. But of course, aviation is about safety, reliability, repeatability. And we want to make sure any standards by the FAA, ICAO, that we meet them and exceed them. So with respect to location and visibility, we have GPS transponders, ADS-B on board, so you can constantly see our balloons. H-ball is our call sign. Lots of people As an example, the government from Puerto Rico, I think, spends more time on Flight Radar 24 looking where our balloons are than we do. Multiple redundant satellite tracking and control plane with Iridium and Inmarsat, radar reflective materials, LED lights across the solar panels so that they can be seen at the required distance away visibly, plus a redundant flight termination system so that we can reliably, when the balloon is finished, because the lift gas is depleted enough that we can bring it down at a time of choosing to a location that we planned ahead of time. And of course, no part of the balloon ever comes apart. The balloon and the payload stay together so that we bring it back as an intact entity. And we've got some mileage under our belt now. We've flown over 1,500 balloons. 27 million, 28 million kilometers. We've been up there for a long time. 700,000 flight hours. So we started out with that rubber balloon I showed you earlier on, but it's a much different picture now. And our record balloon now is just shy of 200 days, at 198 days. We often fly balloons over 100 days, and our objective is to increase that even further, 300 or even 300 plus days. So with that, I'd like to say thank you, of course, to the United Nations, ICAO, all the member states and the ANSPs, critical to our success. And anybody that's not connected with us today, we invite you. Please reach out to myself. Our marketing person, Janine, is here. Matt Mulhern, who runs operations. We'd love to talk to you. Thank you.
Thank you, Alistair. And next is, I'd like to introduce Etienne. So Etienne Barreau is the director of Project Stratobus. And I think he gets the cool award for the coolest video. Just wait. Thales Alenia Space Exploration and the high altitude platform there. Over to you, Etienne.
Thank you very much, Nancy. Okay, let me start with that. Oops. Okay, so yeah, one correction here. I'm not the director of the project Stratobus. I'm its representative here, and a director of an innovation center in Boston. Thank you, Nancy. So I'm going to talk about our great project Stratobus from Thales Alenia Space and start with a video that is going to show you what is Stratobus, what's its mission, and how it works. And then I will shift to some key insights to share with you about navigation and the program. Here it is. Stratobus can fulfill many type of missions, and our idea is that the payload be plug and play, meaning that anyone can bring a payload and attach it to the Stratobus for a very easy mission preparation. Okay, so let's switch to the presentation now. So some insights about where we are in the program, what are our target dates, and a few points regarding navigation. Okay, so our goal is to have a first reduced scale demonstrator of technology by 2019 and do flight and demonstrate the technology. And then the first prototype flight model flying in 2021 with all the required certification. And we have started work with the EASA on that, and now starting with ICAO. And just afterwards, so after 2021, entering commercial phase and selling the Stratobus to whoever would like to buy it and operate it around the world. So we foresee several mission profiles, local missions first, meaning that the Stratobus is within line of sight of its base station and ground control segment. National or regional missions, where the area of operation is further away, and so Stratobus will lift off, reach the stratosphere, and then transfer from there to its area of operation. That could be typically a border, a strait, whatever, and stay there with remote communication means. And at last, worldwide mission, meaning after liftoff and reaching the stratosphere, Stratobus would be able to transit around the world over oceans or over countries, assuming that, of course, we have to respect the air navigation rules among these countries, and, of course, to get agreements for transiting over. So these are three different types of missions. How do we keep control with Stratobus during that time? Either through, at least, for the telecommand and control, through direct radio links or through satellite links. And the point is that during all the transfer, we move from a contact to the main ground control segment, to a satellite control, and then to hand over at the end to a final ground control segment, if any, or remaining on remote satellite links if no final ground control. So this is about communication with Stratobus for keeping the control. Important important points, ascent and descent phase, which is a key part of the mission. So it's very important for us, in order to fulfill our mission and our commercial purpose, to be able to take off and land from any suitable place and to transit safely, of course, through the navigation airspace environment up to the stratosphere. So that's critical to the fulfilling of our mission purpose. The point is that, like any other balloon or blimp airship, Stratobus has a very limited maneuverability in English, especially during transition phase. Typically, a Stratobus will be sensitive to fine weather windows. Its trajectory will depend on the wind. An ascent phase will be typically of 2 hours with specific trajectory. It can be interrupted shortly. The descent phase is typically 6 hours with specific trajectory and little opportunity to interrupt this descent. And our point here is that this set of constraints, but must of course be taken into account in the CONOPS definition and in the organization of the navigation and safety rules. And here I'm referring to the management of other airships, typically definition of segregated airspace or safety volume or whatever suitable alternative around Stratobus during this transfer. What are the requirements on navigation equipment, transponder, anti-collision and navigation lights, whatever. Of course, we are thinking about having all of that on board. And what will be the principle of interfaces with air traffic control and other bodies for emergency situations. So this is for the ascent and descent phase. Now, operation is in the stratosphere. So one point here is that Stratobus is very stable in the stratosphere. It's easy to keep it up there. It's lighter than the air, and it will be willing to stay there almost forever. For that reason and others, the operations activities are very similar to those of satellites in many aspects. And we are very used to make satellites. There is a very high level of onboard automation. Everything is about pre-programmed kinematics and motions, either to stay at a position or to change location. And meaning that a fleet of Stratobus and an entire fleet could be managed routinely through a centralized control center with a very limited number of pilots at any time, except during specific situations, of course, but like one person could handle a fleet of 15 Stratobus at a time. That being said, the key point for all of us around this table is that we all share the airspace together. And it raises a question that we are beginning to address about which navigation rules for Stratobus, which control implementation, is it delegated to each airship control, Stratobus control, or centralized by air traffic control, or how does that all work in the stratosphere? And what are the requirements, again, on navigation equipment on all airships up there in the stratosphere? And a souvenir of one of the, probably the first blimp balloon ever in 1885 here. And on that last photo, sorry, I didn't switch on that. Here we go. And that's it for my presentation. And I would like to thank you very much and for listening to my presentation. And of course, I'm open to any discussion with any of you. Thank you.
Thank you, Etienne. Thank you, Etienne. So, how many of you have regulations in place for this now? I know many of you do, right? Okay, we got some work to do. So those are two things that may look slightly unfamiliar to you. Now we'll move to the things that look a little more familiar to you. So we went from the US to Europe and now back to the US. So let me introduce Martin Gomez. He's the Vice President and Program Manager for Project Aquila. Aquila is a high altitude platform as well. Looks a little more like what you're familiar to seeing, only it's really new and cool as well. Do note, though, the very, very near-term implementation dates. And these guys aren't blowing smoke. They're serious. So this is private funds, private money, private investment, and when you do it that way, it's usually on time. So over to you, Martin.
Thank you, Nancy. I'm actually not a vice president. At Facebook, the vice presidents don't dress like this.
Do they dress in shorts?
And flip-flops, yeah.
Flip-flops and shorts.
Well, first, I wanted to thank you. I'm here with my colleague, David Hansel, and on behalf of Facebook, we want to thank ICAO for the invitation to be here, and we wanted to thank you for your attendance. Merci beaucoup pour votre participation. And I won't insult the language of Voltaire any further. So, Facebook is a very, very mission-driven company. Our mission, like ICAO's, is to bring people together. Formally, is to give people the power to build community and to bring the world closer together. This is very difficult to do at scale. We, as we discussed, more than half the world is not connected to the internet, so it's even harder to do for them. But even for the 3 billion that are on the internet, by the way, Facebook already connects 2 billion of them. Even that's hard. It just gets harder and harder as you move further from big cities and from the developed countries. And the next challenge for us is exactly that, to bring internet to places where we don't have it today. So the green arc are those of us who have good internet, and the red arc are those of us who don't. So it gets harder when you consider that most of the people who don't have internet access live in developing countries. And the numbers at the bottom are some of the more compelling ones. It shows that the rate of adoption is slowing. Being just a dumb engineer, I put this spin on that. We have connected the ones who are easy to connected, and every subsequent connection gets harder and harder. We've plucked the low-hanging fruit, essentially. We are also, aside from being very mission-driven, Facebook is very data-driven. And this is one of the many ways in which we slice and dice the world. We look at it by what kind of connection do our users use when they connect themselves to our products. And obviously in North America, we have excellent connections. Most of Western Europe has excellent connections. But look at the billion people living in India. That is a 2G connection, and if you don't speak the connectivity language, let me translate. That's like a dial-up modem from 20-something years ago. We have stories of Facebook users in India who do this. They take their phone and put it on their nightstand and set it so that it keeps connecting, okay? And they let it run all night so that in the morning they can read their news feed. That's something that for me here takes about 3 or 4 seconds. So in India, you can see there's a great deal of connectivity is just slow, and they are not atypical. And a lot of that is because even though there might be a cell phone tower, there just isn't good backhaul. So backhaul is one of the things that we want to do to help connect people. We don't believe for a minute that there's only one way, that a UAV is the answer to every problem. So in particular, if you're in a densely populated city, the answer might be a terrestrial mechanism. You may have heard of some of Facebook's work in this domain, where essentially we put Wi-Fi on every street lamp, okay? Using wavelengths that don't go very far so that they don't interfere with one another. But as you go farther and farther from big cities and the population density starts to drop, that doesn't work very well. And if you go all the way to the right on this image, where you're in a very rural area, a satellite might, wrong picture. A satellite might be the right way to do it. There is a limit, however, to how many bits per second you can deliver through a satellite. So in between the very low density populations of the rural areas and the very high population densities of a city is the sweet spot for an unmanned aerial vehicle. And in the middle of this is the constellation of Aquilas. We intend to cover remote areas about 50 kilometers in diameter with one UAV that lingers in an orbit there for about 3 months. It's at very high altitude. It's never below flight level 600. If you study solar-powered airplanes for about 1 hour, you come to the conclusion that they are enormous and very lightweight. Aquila, which is only our first solar-powered UAV and is not our last, has the wingspan of an airliner, about roughly a 737, maybe a little more, but it only weighs 400 kilos. So that the ratio between the weight and the wing area is everything to an aircraft designer. An airliner, each square foot of the wing carries about 100 pounds. In a 2-seat trainer like a Cessna 152, it's about 10 pounds per square foot. We have to be below 1 pound per square foot in order to be able to extract enough energy from the sun to power the airplane during the day and charge the battery so we can fly at night. 1 pound per square foot is about a hang glider or maybe less. So our first airplane looks like this. It's a little bit peculiar in that it is a flying wing. It has no empennage and no fuselage. Essentially, the wingtips act like the empennage. It is, of course, made out of carbon fiber, and it's very big and very flexible. It would fit in this room this way, okay? But like I said, subsequent airplanes will probably have to be even larger. And it's very flexible. These do not make for easy aircraft design challenges. Needless to say, the existing aircraft certification rules were not designed for aircraft like this. It's also extremely slow. One of the things that you learn on the second hour of working on solar-powered airplanes is that they fly at about 20 knots equivalent airspeed. That's actually fast. 15 knots it would be better. So the way we connect people with this is like this. One airplane will be near an area that currently has very good internet. Let's say, I grew up in Latin America, and I've noticed back in the 70s, it was not uncommon for a lot of services to stop at the border of the capital city. Back then, the telephone system would stop shortly thereafter. The power grid would stop shortly around there. And even in this day and age, many times good internet stops at the border of a big city. So how do you take internet the rest of the way? Because there are people who are far from the capital cities. Well, our architecture is a microwave link to the first airplane in the chain, which is connected to the internet gateway you see here. That airplane is going to circle in that 3-kilometer orbit more or less indefinitely, call it 3 months at a time. And it connects to other aircraft in the constellation using an aircraft-to-aircraft link, which is free space optics, namely laser communication. And all of those serve a particular community where there are enough people to justify the economics of having an airplane dedicated to them. are still working on the business model. Are we going to go directly to a user handset the way Loon does? Or are we going to provide the backhaul for those communities where they have already good infrastructure locally, but they're just not well connected to the next big city? In those cases, so the answer will probably be all of that, depending on where we are on the planet. The aircraft work kind of like this. We expect, this is anathema under current regulations, we recognize this, but we expect to have multiple aircraft per operator. The economics do not scale if you have to have one or more pilots per aircraft. And we expect them to be consolidated in a fleet operations center. The aircraft will not be at airports, at traditional airports. The services that come with an airport are not what we need. We need runways that are short but wide. We need enormous hangars. If you can think of a World War I aerodrome, basically a 300 or 400 meter diameter circle of grass, that's best, because these aircraft do not tolerate a crosswind. And of course, normal airports are full of normal aircraft, which is the last thing we want when we fly at 20 knots. The idea is that we will climb in some segregated airspace until we're well above all air traffic. As you know, flight level 600 and above is lightly used but not unoccupied. There are people there even today. Before the advent of all of us, that airspace was not empty. Once it's above most air traffic, it'll transit to the location where the service is needed. The thing to remember is these airplanes move slowly. Going upwind, our ground speed could be roughly like Loon's, okay? Except they don't go well upwind. But we want to fly very, very slowly and preferably go downwind. Once we're there, we simply fly inside a cylinder that's 3 kilometers in radius where we provide our service. And we stay there for 3 months and then repeat the process in reverse. The other thing that we should add, solar-powered airplanes don't do anything quickly. They don't climb quickly. They don't descend quickly. They're not developed quickly. And they also tend to not want to hold altitude. One of the techniques we use to make up for the weaknesses in current batteries is to let the aircraft float up during the day and descend at night. In other words, store energy in gravity. It lets us rely on less good batteries so that we don't have to wait for the better batteries to show up. So that means if you ask us, please climb and maintain 10,000 feet or so, we can do that up to a point. But once we're above flight level 600, we are going to want to float up in the day and descend at night. And of course, the airspace is lightly enough used that we should be able to work something out with a local ATC. Okay, we don't want to take up too much of your time. We just wanted to end with some beautiful photos of our beautiful airplane. This is on some of our test flights in Yuma, Arizona. And we look forward to answering your questions over the next couple of days. Thank you very much.
Thank you so much, Martin. So I promoted everybody else, so now I'm going to introduce the president of Airbus. And he's going to talk to you a little bit about the high-altitude platform that Airbus is planning and is ready to put into research trials very quickly. Just before I do that, let me ask you, are you getting nervous? So the good news is they're not looking to have flight level 450 expanded and air traffic control services provided like you think of them today at flight level 600. They're not. They're looking to work together as a community to begin to put together a relatively autonomous capability that they will demonstrate to you through a series of tests, which is quite different than what you will have seen in the past. Not unlike what's happening today below flight level 400 in parts of the world today for small UAVs. So with that, Andrew's going to answer, Andy, the president of Airbus, is going to answer all of your questions related to that particular product. Over to you.
Despite Nancy's aspirations for my career success, I am actually the head of flying for the Airbus ZEPHYR high-altitude pseudo-satellite program, and I need to work out how to drive this video. Is it that one to go forward? Yeah, okay. So, I must say that I am quite enjoying the irony today of an ex-helicopter pilot who gets a nosebleed above about 2,000 feet delivering a presentation in this session. But what I want to talk about is the Airbus ZEPHYR high-altitude pseudo-satellite. Going to give you an insight into its characteristics and its concept of operations, much of which will now sound very familiar. Thank you, Martin. But the main focus of my talk is going to be on how I think HAPs, as we call them, might be safely accommodated in the near term in what I'm going to call higher airspace, because I can. And I hope the intended meaning of that term will become clear as we go through the talk. So I think you've got the idea as to what these things are. Many of this afternoon's speakers are seeking to do the same thing as we, that is to put a viable payload over a mission area persistently and economically. But the Airbus solution is similar to what you've just heard. It is a solar electric powered, very long endurance, remotely piloted air vehicle, which will fly in the stratosphere, largely above the weather and above other air traffic for many weeks and months. The point here being that something like ZEPHYR combines the focus and redeployability of an aircraft with the persistence and global coverage of a satellite at relatively low cost compared to both. So compared to our 2010 era ZEPHYR 7 prototype, today's ZEPHYR S for single tail, has advanced considerably with much better performance and very considerable automation. ZEPHYR S is in low rate initial production and will be fully operationally capable next year. The larger ZEPHYR T is currently in development. We will be flying ZEPHYR S continuously for several weeks next year on a number of occasions, intending to conduct international operations and to exercise the full capability that I'm about to talk about. Yuri, could you please play the video? So let me first explain a little bit about ZEPHYR over this short video, which was taken from our world record flight. The aircraft still holds the world record for aeroplane endurance. Key to success is efficiency in every respect: solar panels, batteries, aerodynamics and structure. Current ZEPHYR S is 25 meters wingspan, 65 kilograms weight, and half of that is batteries. A bit like a killer, it flies at 15 knots equivalent airspeed, and as you can see, we're currently hand launched, but in future we'll be using a launcher system. During the day, the solar panels on the wing gather energy, and we use the excess energy to get us into the stratosphere, typically above about flight level 700, with fully charged batteries at the end of day one. And then to descend overnight to conserve power to a predetermined dawn altitude, which will typically be above flight level 600, and thus begins the now familiar diurnal cycle of charge and climb in the day and descend and discharge during the night. ZEPHYR is highly automated, but it is most certainly not autonomous, and there is always a human crew in the loop. As you can see, we recover conventionally, typically at dawn to get the best of the calm conditions, and the aircraft is then landed for refit and ready to go again. Key point here is the unusual flight profile of ZEPHYR, which naturally separates it for most of the time from most other air traffic. So just let me summarize a few key points about how it flies and what its characteristics are. First thing, again, is that very slow flight. 50, maybe 60 knots true airspeed when it's up in the stratosphere at very high altitude, almost pseudo-stationary. Limited maneuverability, doesn't go very fast, therefore, although the turn radius is very small, it doesn't actually go anywhere, so it behaves very differently to conventional aircraft. Rarely at constant altitude, either going up or going down at very slow rates. That said, we can also stay within an assigned altitude block for a certain amount of time. Can be affected by the wind, may not therefore follow a precise track, and most certainly therefore cannot conform with the normal expectations for IFR flight. But to bear in mind, please, that 99% of a HAPS flight, at least, is well above other air traffic. We spend weeks in my higher airspace and only a few hours in conventional lower and upper airspace. So now, the laws of physics being what they are, we need sunlight, and that does constrain where we can fly. We talk about a mid-latitude year-round capability and a high-latitude seasonal capability, and our intent is to place strategic HAPS operating bases at relatively low latitudes in order to get the best of the sunlight. We envisage a few centralized mission control centers using beyond radio line of sight communications to enable global operations in support of mission delivery lasting weeks and months. And we obviously need to be able to move the RPA around the world in order to maintain continuous coverage. For planning purposes, we imagine moving the aircraft around at about 1,000 miles per day. And we will shuttle multiple RPA in order to maintain coverage over a particular mission area. Now, ZEPHYR crewing and flight management is a rather multi-dimensional affair. ZEPHYR is a distributed system, so the traditional model of one-to-one pilots to aircraft, point-to-point, doesn't work for us. The economics, as we've heard, don't stack up. And so the pilot of the aircraft and the aircraft itself may well be in a completely different region of the world, conceptually much more akin to satellite operations. The missions are very long. There are going to be an awful lot of shifts and changeovers. We call them flight segments, and therefore an awful lot of handovers between different crews and different mission centers around the world, which we obviously need to make as transparent as possible to air traffic control. That's a big challenge. And finally, we also intend to operate the aircraft in what we call constellations, with multiple aircraft linked to single ground control stations and therefore single crews. Okay, so I'd like to turn my attention now to how I think we can safely accommodate HAPS and comparable operations into higher airspace in the near term. There are a few key attributes to note, some of which will now sound familiar to you. The first thing, we do not need to operate in proximity to other aviation. In fact, we will go out of our way to avoid it. Please don't take that personally. Our operating bases will be remote from busy airports, and we will intend to place the climb and descent zones and areas well away from busy upper and lower airspace. Secondly, guess what? Nothing happens quickly. So HAPS can be managed almost like a pseudo-stationary obstacle. And the climb and descent can actually be fairly readily managed through standard air traffic management practice, possibly using bespoke separation criteria and notified corridors. And finally, we can recognize problems and abnormal interactions with lower and upper airspace can be predicted, and the risk of those abnormal interactions can be managed. Now, there aren't very many of us at the moment that are capable of maintaining sustained operations up in higher airspace. So the proposal here is that we are accredited, if you like, we can be trusted, at least for the time being, to self-separate through coordination, conspicuity, and competence, and the assured prediction of anomalous vehicle behavior. It's therefore my assertion that the complicated framework of classical IFR is not necessary for HAPS and similar craft to remain safe in higher airspace. There is a better way of doing it. So let's talk about my wish list. I call it enablers for safe HAPS, higher airspace accommodation. First thing we need to do is to work with air traffic authorities and ANSPs to make it possible to access higher airspace safely and easily. And above all, guys, we need to avoid the need, wherever possible, for formal airspace change, because that will kill the flexibility that we need. We will probably have to implement some special conditions, but we need to do that only where it is strictly necessary to assure safety. We can define the boundary of higher airspace above which HAPS can manoeuvre relatively freely. And my suggestion is that this is not a standard number. This is based on real-world traffic patterns, which may well vary between different locations. And so we can tailor it according to the requirements of a particular region. We can establish a user-centric approach to keeping out of each other's way. Something like the time-bound booking of higher airspace, but that is not formal segregated airspace. Let's use the NOTAM system and the flight planning system to let everybody know what we're doing. The reality at the moment is that we need to establish multiple bilateral agreements in order to cross airspace management boundaries. Takes too long. It would be really good if we could standardize some sort of protocols for operating in higher airspace so that the act of crossing an FIR boundary, for example, or the upwards extrapolation of an FIR boundary could be made much easier. Having said that, I too recognise that there are issues of sovereignty and overflight privileges which also need to be very carefully considered. And finally, we do recognise that it's possible that a struggling HAPS might arrive in upper airspace unexpectedly, and we therefore need to be able to facilitate air traffic cooperation and coordination in the event of abnormal system behaviour. That is not as daunting as it may sound, because in most circumstances we can predict such a descent well in advance. We know what is going to happen. So let me finish off by proposing what I've rather grandiosely called a new paradigm for higher airspace, and I've given it a name: open flight rules. OFR, not an upwards extrapolation of IFR, not about segregated airspace, but a tool set of adaptable higher airspace deconfliction measures exploited by an accredited user community. It could be largely self-managing with minimal ANSP involvement during normal operations, and ideally it should be universal so as to minimize that overhead for everybody, ANSPs and us alike, of crossing between the jurisdiction of multiple air traffic authorities. And this is where industry needs help to help itself. ICAO has already produced a lot of great guidance as far as RPAS operations are concerned, and that's made some of the operations that we've been talking about today possible. But the focus for ICAO is very understandably on upper airspace integration. What I'm proposing is that a small adjustment to that priority would be extremely helpful and would actually be an enabler for this exciting new sector of aviation. Thank you.
Thank you very much, Mr. President.
You're welcome, Mark.
Thank you very much, Mr. President of Airbus. That's awesome. So it's actually 3 o'clock right now. That's our break time. But what I would propose to you, I notice that you're raptured by this discussion, as am I. So what I would propose is we take one more 15 minutes and then take our a short break of 20 and continue. You okay with that? If you're not, and you need to do whatever you need to do. Okay. So let me now introduce Leon Travis. So I'm going to promote him as well. Today, he is the Chief Technology Officer for Worldview. Actually, that would be Tabor McCallum, but Tabor had a very important launch today, so he wasn't able to be here. So today, you're officially the Chief Technical Officer of Worldview. He's going to talk to you a little bit about interspace tourism.
Well, thank you very much, Nancy, for the promotion. I'll forward that to Tabor so we can adjust the pay appropriately by the end of the month. And thanks everyone, for being here. A great panel, and actually, contrary to the introduction, I'm probably going to speak a little bit more about our commercial uncrewed application today, because we see that as having probably the most heritage to date, and the one that's going to be of a near term in terms of priority in working out how to work in this airspace. I lost the clicker.
Take the clicker.
Ah.
Oh, you're demoted now.
Thank you. Oh, okay, fantastic. All right, so to understand worldview is to understand where it came from, the StratX program, which was stratospheric exploration. It was culminated in a series of 3 flights with Alan Eustace, a former Google executive, and spearheaded by Tabor McCallum, who was at the time the CEO of the Paragon Space Development Corporation. Together, they put together this wonderful vehicle, which consisted of a bespoke spacesuit for Alan, and then took that to the upper reaches. Here you can see some attitude, determination, and control testing there of the suit. And there's another shot there of the suit in the Smithsonian with our CEO, Jane Pointer, Alan, Dr. George Neal, Associate Administrator for the FAA, and of course Tabor on the right. So a few things that we achieved through the StratX program, the most grand of which being the altitude record, 136,400 feet. And Alan was safely returned to Earth. Everyone's pretty happy to hear about that. But the StratX team then formed is the basis of Worldview. Here you can see our facility in southern Tucson. Giant launch pad there. You can see a balloon beginning to be stood up. And where we do design, manufacture, test, integration, and launch of our balloons, and in particular Stratolite. This is a persistent vehicle that travels into the operates between about 50 and 100,000 feet. We recently managed up to 5 days of continuous flight before electing to terminate the flight. We managed to learn a great number of things about how to operate in that upper atmosphere. Some key points about the vehicle being that we see it as rivalrous to high altitude conventional UAVs. Obviously we've got some new competition in that realm as well, but unconstrained by orbital mechanics and can operate at a low altitude than say CubeSats. In terms of applications, weather is obvious, being able to persist over a tropical storm, for example, and see it as it develops and characterize it deeply. So with radar, we see as having considerable benefit, as well as marine domain awareness and remote sensing applications. A little bit on the vehicle itself. You'll notice our propulsion module is uppermost there. It's a rather long flight train, about 400 feet. And there are the solar panels and a stratocraft at the base. It's a closer shot of the stratocraft itself at the facility. And you'll see the solar panels. So we can actually rotate the balloon and point to get the greatest flux density on those panels. And you'll see on the base of the stratocraft itself is where we will host the payload. A bit more on specifications. Okay, so currently hosting around about 50 kilos. Going to bump that up again and double it again next year. 250 watts continuous, which seems to be quite a good power output for that size vehicle, the trade with mass, etc. And again, I mentioned operating between 50 and 100,000 feet, which being here today is relevant. It's very much in our backyard, so to speak. So we're very interested in what evolves here. A key point about this too is that come time for termination of the flight, we actually recover the payload intact using a steered parafoil. So talk a little bit about this aerodynamic descent system. As you can see, as I mentioned, so it is steered, and we will decide and coordinate with air traffic management, in particular the center, for example, Albuquerque or Salt Lake City or LA even, and this has been in our recent efforts, and coordinate ahead of time that termination. We'll then terminate the the flight, separate the stratocraft at altitude above FL600, and then fly it downrange to a predetermined landing zone. The balloon carcass itself will then descend again to an area that we've defined through a notice to airmen as an intended landing zone. So a little bit, just a quick video here showing you that that's our custom facility. You see, as I said, we do our own manufacturing. This is an example here of the craft being stood up, and you'll see it come off the spool shortly. Again, this is a collage of a few flights, but that being Page in Northern Arizona. We do this in coordination with air traffic control, so the tower is in complete control of the process. It's at the point that we've agreed that we are safe, the traffic is clear, and then we will send some in-flight. So yes, the magic, so to speak, how do we steer the balloon? So again, we ride this air current and up and down, and we call it a barber pole. We can go up and down and pick a northerly, southerly, east, west, etc. trajectory, and that affords us the ability to persist over an area of operations. And we're getting a little bit cleaner with the payload deck, and this is an example of recent remote sensing work that we did in southern Arizona. And as I mentioned there, here's the termination phase, again in coordination with the relevant center and special use areas, and it's quite a gentle landing, as you can see there. So that's that.
Can you say a few words about the space tourism?
So yes, I intend to talk tomorrow in the panel about space tourism.
Okay,
but
so that's a teaser for you tomorrow. You'll get it tomorrow in the.
And there's another video. So yeah, but again, so the reason why we're here, safety, safety, safety. Of course, we're very interested in conducting our operations in coordination with other users of the airspace, and doing so in a collaborative way. And what we know, though, is that until, well, there still remains no consensus on the limit of state sovereignty, let alone the definition of vehicles, which we know is evolving. You have, especially with respect to space launch systems, there are a number of hybrid vehicles, suborbital, coming along line, as well as the space balloon. So some of these things to think about are this collision assessment, being able to understand the likelihood of conjunction, the ability to absorb and trust data in real time, the ability to handle off-nominal events as well as those planned, and of course prioritizing the uninvolved third party, the public. Mention the so with regards to data sharing, confidentiality is quite important, so that there is trust in the accuracy of this, and as well we seek to not look at a light touch with regulations, and of course whatever we choose to decide has to be consistent with existing treaties that are already in place, and we don't want to step into those realms. So what if we could take an existing space situational awareness solution and bring it down to FL600, something that could provide the conjunction assessment, certainly at least provide a operational database of contacts amongst the operators and their navigation service providers. So one option is to work with the Space Data Association, who has expressed an interest in looking at bringing their services down to these levels. Formal organization that's already working well with commercial, civil and military satellite operators, and it's a run out of the Isle of Man. So if anyone knows anything about the NDAs that the Isle of Man has, enforces, there's quite a penalty for misusing the agreement. So trust being paramount in the sharing of data between operators. They also have a very powerful tool set in which to do that conjunction analysis. They do so for spacecraft already and launches. And as I mentioned, I've been doing for some time, as well as the ability to forecast and provide some analysis of radio frequency interference. And the Space Data Center itself being one might envisage, and these are just ideas, one might envisage that the SDC could itself be a single point of contact for air navigation service providers. So with that, I'd just like to also say thank you very much for the opportunity to speak here today, to my fellow panel members and to Nancy for chairing this. And we'll be here all week, and very much look forward to the lively discussion that's going to continue.
Thank you. Thanks very much, Leon. Okay, so now you have deserved a break. We will thank ACI for the break that's upcoming and come back in 20 minutes. And Dr. Liu will then give his presentation, and that'll be very interesting, so don't miss that. Back in 20.